So I think we should probably begin. It's a real pleasure to introduce Michael Conroy, who's a postdoc here at Arizona for a couple of years, and he'll be moving on to Clemson University as a faculty member there, and he'll be talking about extreme values in the symmetric exclusion process. So Michael, please begin when you're ready. Okay.
Thank you. Happy to be here talking about this. A lot of stuff I'm going to talk about today is joint work with Sunder. So let me start with the model considering the simple exclusion process on the integers with a step initial profile. So this is a initial condition where we place a particle at every non-positive integer with no particles to the right. So the system has infinitely many particles, and there is nearest neighbor interaction only, and this is exclusion process. So any jump, so each particle has a clock that when it rings, it tries to make a jump to the left or right, and it can't occupy the same spot as another particle. So in the case I'm going to talk about today, which is symmetric exclusion, particles will tend to spread out to the right because leftward motion is blocked. Oh, by the way, feel free to interrupt with any questions at any point if anything's not clear. So in the symmetric translation invariant case, we can tag the leading particle to the particle that's initially at 0. And since particles don't change order, this is just the maximum position in Z where the occupation variable is 1. And we're going to consider the behavior of this tagged particle as time goes to infinity. So the motivation for this was looking back at this paper of Arratia in 1983, where he considered the same step profile, but with independent particles instead of particles in exclusion interaction. And he described it as a comparison result for exclusion. So now we place a continuous time simple random walk at every non-positive integer. All these are independent, and we can look at the maximum. So this is not a tagged particle because as independent particles, they can get all mixed up. And we're going to look at the front of the particles as they're spreading to the right. So Arratia's theorem was a law of large numbers and essential limit theorem type result for this maximum. And notably in the limit, the particle has a Gumbel distribution when it has appropriate scaling. So the Gumbel distribution is a classical extreme value distribution. And Arratia also proved that the same law of large numbers behavior holds for the tagged particle that starts at 0 in the exclusion system. Okay, so the law of large numbers results say that this particle motion, this particle position is on the order of square root of t log t. And a natural question is, well, does this Gumbel result hold as well? And it turns out it does. So to see why it happens in the independent case, we can reframe this as a question about a Poisson limit theorem. So if we want to analyze an event where xt is smaller than some value, that's the same as saying no particles have moved to the right beyond Z. So this is true in the exclusion system because no particles can pass that one. And it's true in the independent system because we're just looking at the maximum. So that's not tracing one individual particle. So in the exclusion system, let n be the number of particles beyond this value bt times x plus at at time t, which can also be represented as a sum of occupation variables beyond z. And z here with this scaling grows like square root of t log t, which is about the order of the position xt. And so we expect in limit n to be of order 1. So in the independent particle system, now I'm going to denote this by a superscript RW for random walk. We can represent this number of particles beyond some level z as a sum of, as counting the number of random walks that have passed. And this is a sum of independent Bernoulli random variables. And we have classical results about Poisson convergence in this case. And if we calculate the mean of this number, then we see we can rewrite these probabilities of random walks starting at I as random walks starting at 0 shifted by I. And we get an expected value of a simple random walk starting at 0 minus z, taking the positive part. Z is of order square root of t log t. So if we divide by square root of t, we have something that tends towards a normal random variable minus the square root of log with the square root of t out front. And by considering normal asymptotics, we can compute the limit. And in terms of x, it's e to the negative x. So we have that the mean converges to e to the minus x. And since z is of order square root of t log t, if we compute the sum of squared expectations of these independent Bernoulli random variables, you notice that they're monotone in I, because a particle starting, or a random walk starting farther to the left, less likely to be a certain amount to the right at a certain time. And so we can bound this by a probability of a random walk bigger than square root of t log t, which tends to 0, times this mean, which has a limit. So for a sum of independent Bernoulli random variables, convergence of the mean and convergence of the sum of squared expectations is sufficient and in fact necessary for Poisson convergence. So this was Arratia's proof. This end tends to Poisson with parameter e to the minus x. And so if we go back to our CDF that we wrote in terms of n, this converges to a Gumbel CDF. So I'm claiming that this holds also in the exclusion system case. But in this case, n, of course, is a sum of correlated Bernoulli random variables. So we can ask why should the same limit hold? Well, for the same scaling. So one reason is that the means have the same expectation for any value of t. And the easiest way to see this is through the stirring construction of the symmetric exclusion process. So the stirring construction is constructed as follows. So we have so-called stirring variables, which I'm going to denote the same as random walks because they're going to have properties of random walks. And we consider now each bond between lattice points as having some independent clock that rings with rate 1/2. And when it rings, values on either side switch. So sorry. So I have a little schematic here about how the stirring process works. So to each particle, initially in the system, we assign a stirring variable, and we can track each bond. And I have a couple time snapshots here. We can track each bond, and these X represents clocks ringing. And at each point, when that rings, say over here, you're going to have the stirring variable starting at -4 and the stirring variable starting at -5 switch. So that corresponds to an attempted jump in the exclusion system. And of course, that doesn't change the system, but in terms of the stirring representation, they have switched places. So the stirring variables don't correspond to the same particle. And if we make all these switches, and then we look at what happens at the end, we see that the order is all stirred up, hence the name. And if we track the trajectory of a single one of these variables, tracking every time it switches over, this looks like the trajectory of a random walk, and in fact it is. So marginally, each of these is a random walk. We can just as well represent the number of particles beyond ZT X in terms of the occupation variables, as well as in terms of the number of stirring variables that have gone beyond Z. So they aren't associated with the same particle in the dynamics, but there is one per particle. And since now we have a sum of these indicator functions, when we take the mean, marginally, each of these is a random walk, and we have the exact same expectation as in the independent particle system. And therefore, the same limit holds. So again, we have this n on order 1, and its mean converges. And so we need to show that, in fact, it is Poisson, and then we have the result. So now we have a sum of correlated Bernoulli random variables. And their correlation is of a specific type. It's well known that they're negatively associated for the symmetric system. So in fact, something stronger is true when the symmetric exclusion system starts initially from a product measure. It has a so-called strong Rayleigh property. So the definition of this property is given in terms of a generating function. So if we define a generating function Q this way, where we initially start with the product measure, then the derivatives of this generating function satisfy a certain inequality. So this applies in our case because the step initial condition is a product measure. It's a product measure where the Bernoulli parameter is 1 to the left of the origin and 0 to the right. And why this is stronger than the negative, or it's stronger than negative correlation. So here's the definition repeated again. And if we plug in ones for all these xi's into this inequality, we just get a negative correlation inequality. And importantly for Poisson convergence is that this property implies that for any sum of these Bernoullis with this property, there exists independent Bernoulli random variables such that the sum has the same distribution as the sum of the independent Bernoulli random variables. So this result doesn't say anything about the marginal distributions or the joint distributions of these independent Bernoullis, just that as a sum, it has the same distribution. So I mentioned earlier what is necessary and sufficient for Poisson convergence of independent Bernoulli random variables. So this relationship will tell us what's necessary and sufficient for Poisson convergence of these correlated strong Rayleigh Bernoulli random variables. So we have convergence of the mean already because the two sums have the same distribution. And what we also needed was the convergence of the sum of squared expectations to 0. Well, if we compute what that is for these zetas, we can write that as the expectation of the mean minus the variance of the sum. And since this has the same distribution as the sum of correlated Bernoulli random variables, we can replace that. And then if we compute out this variance, we see that this is exactly equal to the sum of squared terms for the correlated Bernoullis minus the covariances. So these are negatively correlated. And so we have a sum of two non-negative things. And so this converges, the sum of the square expectations for the independent Bernoullis converges exactly when the same does for the correlated Bernoullis, and also the sum of covariances converge to 0. So showing that the sum of squared expectations vanishes is easy. It follows almost exactly like in the independent particle case. Once you write these occupation variables in terms of stirring particles. And the difficult part is dealing with these covariances. So to do this, we do a calculation using duality. And the form of duality we use is this one where the expected value of an occupation variable when the system starts at some configuration eta is equal to the expected value when continuous time simple random walk starts at k of that configuration at the point where the simple random walk is. So what that gives us is the ability to compute this covariance sum as a sum of an integral of random walk probabilities. And so this dealing with this is fairly difficult. We need pretty tight bounds, local central limit theorems, things like this for random walks. But we're actually able to obtain an order of convergence, showing that this covariance does vanish. So this shows this same Gumbel result with the same scaling as in the independent particle case. And a couple comments, the results hold more generally. So we don't need a full step profile. We can have holes as long as the initial measure is of product form, because this is where the strong Rayleigh property comes from or relies on. And we need the particle density to be approximately uniform. So in our paper, our condition is a periodicity condition on the Bernoulli parameters. So for example, if left of the origin, if right of the origin, we have no particles, and left of the origin, we have a Bernoulli row product distribution, then that row parameter ends up here in the Gumbel distribution. This is a shift of the mean of the Gumbel. And we can consider things like alternating, right? So say there's a particle on every odd negative integer and no particle on every even, the average particle density is a half, and we get a half that shows up there. So we can do any periodic initial condition. That's periodic left of the origin. The result is also true for more general symmetric jump probabilities. They don't need to be nearest neighbor. They can even be infinite range. So we assume a finite moment generating function for some positive value. And the way the result changes there is we scale by the standard deviation of the random walk jump probabilities. And that also shows up as a shift of the mean of the Gumbel distribution. So importantly, when we go to more general symmetric jumps that aren't nearest neighbor, we no longer have a result about a tagged particle. Since now the particles can change position, this is just a result about the maximum or the front of the motion to the right. So if we go back to the nearest neighbor case with a full step or a particle at every non-positive integer, we can also consider order statistics. So when we had convergence, or when we showed this result for the leading particle, we just needed convergence of the probability that n was 0. So what we actually proved was much stronger, right? That we have full convergence of the law of n. And so what we can do is by considering the order statistics, any tagged particle position is an order statistic. And since we have convergence and distribution of n, we can rewrite the CDFs of all these order statistics in terms of a probability involving n, and we also have that convergence. So we have the limiting distribution of any tagged particle in that case. And we can consider order statistics in the non-nearest neighbor case. They're not tagged particles anymore, but we would still have something similar where the standard deviation would show up in a similar spot multiplied by the e to the minus x. So an intuition for why an extreme value distribution arises in a system is we can think of this mass of particles to the left of the origin, sort of pushing the leader to the right through a mechanism of blocking leftward motion. So we thought about how to probe the influence, like how far does this influence extend to the left? So we consider a sequence of exclusion processes indexed by initial condition, where instead of now a step profile, we have a block of L particles between minus LT and 0. And we're considering now an array. So we want the convergence of the leading particle as the initial condition is changing. And we ask the question, how slowly can this LT go to infinity where we still get the same behavior? And this will give us, in a sense, how far the influence extends. So our result is that with the same scaling as in both the independent particle case and the exclusion case with the full step or a particle at every non-positive integer, if L is diverging faster than square root of t over square root of log t, then we get the exact same limit. And there's an edge case where if LT is on the order of square root of t over square root of log t, then we get a Gumbel distribution again with another shifted mean. That's in terms of that limit. And so what this says is that we can interpret this as the influence is about of order square root of t over square root of log t back into the mass of particles. And what's sort of interesting is that we actually can get a Gumbel distribution in the limit no matter how slowly L diverges. So if L diverges more slowly than square root of t over square root of log t, then we can get a Gumbel distribution. We just need to change the scaling, and the scaling depends on that rate that L diverges. So in this situation, our leading particle is on the order of square root of t times log of L. And all these results with this L step, which we call it, these also extend to more general jump distributions and more general initial conditions. So as long as there are no particles to the left of minus L and no particles to the right of 0, and in between the initial condition is periodic, we get similar results. We get, and by that I mean also a Gumbel distribution with where it changes similar to how it changed in the other case. So Also notably, right, since we prove this by showing convergence of a sum of Bernoulli random variables, this also implies that the same thing holds for the independent particles, right? Anything we prove about the exclusion system also has to hold for independent particles, because that just involves proving convergence of the mean, which we have to do here, and convergence of the sum of squares terms, which we have to do here also. We just don't need to analyze covariances because they're zero. So I want to make a remark about ASEP. So it's known what happens in the ASEP case of the system. So the case where there's a bias to the right was done by Tracy and Whittam in 2009. And in that case, the leading particle is of order T. And they give the limiting distributions in terms of a Friedel determinant. And the bias to the left case, so particles cannot move to the left in this nearest neighbor case. And so with the bias to the left, you expect this leading particle to be on order 1. It's not going to really move very far. And this is sort of given implicitly in Liggett's book, but in our paper, we wrote it and proved explicitly that the unscaled leading particle position has a limit distribution that is the sum of independent geometric random variables. So we prove this by considering mapping to a zero range process, which is irreducible and therefore has a unique stationary distribution, which we compute. And this limiting distribution is given in terms of that stationary distribution. So some things that we're working on right now is extensions in higher dimensions. So the first question when considering that is, what is the equivalent of a step in, say, Z2? So naturally you think, okay, so a half space. But if you think about what happens, particles are blocked from moving left. And since we're only looking at the motion in one direction, we're looking at a projection down onto the first axis. And what you have there is then an infinite number of exponential clocks. And so what you'll actually have is just that the number beyond any level is infinite for any time. And in a calculation, you can see this by, if you calculate the number beyond some z, regardless of scaling, you're summing over all lattice points in Z2 of a projection of a random walk in Z2 onto its first component. And these probabilities don't depend on K. And so you get that the expectation of the number beyond any level is infinite for any finite T. So we make an adjustment, and to get a finite maximum, we consider a variation of a half space where we make sure that there is a well-defined leading particle or leading finite collection of particles. So we can consider some wedge where we have some arbitrary slope S, and we have a particle on the left or below and above these lines. Then xt is the maximum of any position of a projection of the occupation variables onto their first component. And we can get a Gumbel law in the limit where the scaling is going to be different. So this notably is not a tagged particle result, because in Z2, there's more room and particles move around each other, even with nearest neighbor interaction. So of note is that this BT scaling term is the same. And what changes are these sort of lower order corrections. So what that means is that this leading particle position in its first component is of the same order as in one dimension of square root of t log t. So we can do this in all dimensions greater than or equal to 2. So by considering the equivalent of this sort of wedge, so in 3 dimensions, it looks sort of like this, some sort of pyramid. And what we get is a Gumbel distribution where the mean and now variance of this limiting distribution is dependent on the dimension. And this BT scaling term is still the same. The dimension comes into the second order corrections, or lower order corrections. So some extensions of this in higher dimensions that considering now is we can consider different shapes in higher dimensions. So things like this, where you have fewer particles than if you had straight lines, reasonable to expect that you should get some sort of similar behavior. When you have something like this, where there's on the right, where there's considerably more particles than with a straight line, I believe this is okay. I haven't totally figured out. I believe this is okay when this growth is like polynomial, but not faster. And something else been thinking about is exclusion on a tree. So say we have a binary tree, like it's pictured here. So we have to figure out what is sort of a step on this graph. Well, the key feature is that you have an infinite mass of particles pushing the particle. So so one model to consider is one where your initial condition depends on time, and it's growing so that in the limit there is an infinite number of particles. How far ahead does the leading particle extend? That's the question. So I want to mention some other Gumbel limits appeared recently. There's edge behavior of eigenvalues in random matrix theory. Also, maximums of large log correlated Gaussian fields, and maximums of branching random walks. Both these latter results involve randomly shifted Gumbel distributions. And a sort of broader question is what sort of other types of symmetric particle systems can you achieve a Gumbel limit? And some considerations for that, well, this strong Rayleigh property gave it in terms of the exclusion process, but in general, it's formulated for Bernoulli random variables. But that's not so limiting, because there are other limit theorems where the sums don't have to be of Bernoulli. So there's this result of Newman that given arrays, say X and W, where marginally these random variables are the same, the W's are independent, and if the X's satisfy a form of negative or positive association, it's a technical form given there, then you have convergence of the sum of X's to some law if and only if the sum of independent random variables converges. So this opens the possibility to results like this in, say, K exclusion, which we've started to think about, and also systems where you say you have opposite of negative association. You have something like an inclusion process or something like this. Also, I think I mentioned this before, but if you're just concerned with the leading particle, convergence of the law of this N is much more than you need. So it's possible that there's some systems where maybe this is not what you have, but you have convergence of this probability, which is what you need to show the limiting law of the leading particle. So these are things we've been starting to think about. So I have a little time, so I can mention a little bit more about this duality computation for the covariance. So we want to show that the sum of these covariances vanish. They're negatively, all these covariances are negative. And so what we do is we write the covariance in terms of using this duality, in terms of expected values in terms of random walks and expected values of products of occupation variables in the exclusion system. And this is a difference of semigroups. One for the U2 is the semigroup for a pair of independent particles on Z, and V2 is the semigroup for a pair of particles with exclusion interaction on Z applied to this function of J and K. And if script U2 denotes the generator associated to the semigroup U2, and script V2 is the generator associated with the semigroup V2, then we can use integration by parts to rewrite this covariance in terms of an integral involving this semigroup V and probabilities of random walks. So this comes from a computation, a generator computation from the third to fourth line. And what we then do is this V2 is known as a symmetric linear operator. And so we can switch the order and now have this V2 applied to this function, which is symmetric and positive definite. And that allows us to bound this V2 semigroup operator applied to this function by the one for independent particles. So this is related to this negative covariance. And that's what gives us the formula here. So this is written for more general P. In the case of nearest neighbor interaction, these probabilities are 0 unless K and J differ by 1. And so you get the formula I think I gave earlier, which allows us to, so in our paper, we analyze this generally, but one can do it slightly more simply for just the nearest neighbor interaction case. So that's the most difficult part of this. So in any extensions to other processes, likely that is also the case too. I think actually there was a typo back here. So there should be a line that if these xi satisfy a form of negative or positive association and the sum of covariances vanish. It's important. Forgot to write that in there, right? So that likely will be the hard part, right? How to show that for any system or for whatever system you're considering. So thank you. This is our paper. Oops. And thank you for listening. Let me know if you have any questions.
All right. Well, let's thank Michael for a very clear and a very nice talk. Thanks, Michael. Could I open the floor? I think we have some time for questions if there are any. Would there be any questions from the audience?
Yeah, I have one if you don't mind.
Sure, of course.
So thank you for a very nice talk. So I came across this strong Rayleigh property recently, and I'm a little bit confused about how it can be used and applied. It seems like it's a very strong property, but so the way you use it here is you have these Bernoulli variables that are just the occupational variables, and you have some negative dependence for those. My question is, So in this case, your Bernoulli variables only depend on the state of your Markov process at the time you're looking at. So you're looking at the covariance between eta t and eta xt and eta 0 t. My question is, it seems like this negative dependence stuff would also apply to other Bernoulli variables that might depend on the trajectory, the time trajectory of a given random walk. Is this true or not? For example, might be more specific. For example, if instead of eta x of t, you're looking at the indicator function that your random walk number k has hit x at some point.
Yeah, that's a good question. So like, for instance, the stirring variables also satisfy a negative correlation inequality. Is that sort of what you mean?
Yeah, but so you can take these stirring variables as fixed time, or you can take them as time trajectories.
All right. Okay.
So for fixed time, you have these negative dependence. Is it also true for a Bernoulli variable that you would build with the time trajectory? Is my question.
I'm not sure. That's a good question.
Okay.
I don't know the answer. Yeah, I'm not sure. That would be interesting though, because that could open up even more possibilities for it to be used for limit theorems like this. There is a question of, does, one thing I have sort of thought about a little bit is there extensions of this, right? So like, since this only applies to Bernoullis, for instance, but that is an interesting extension as well. I don't know the answer.
Okay. Oh, thank you.
I don't understand very well your result. Your correction terms A and B is the same for the independent random walks?
Yes.
It's equal.
Equal. Exactly equal. Yes.
So, and you understand what happens in the random walk, like if this maximum is due to one particle that goes and be very far away from the others and carry the maximums, you have this kind of result?
Yes.
Or
so
no?
your question is why is the scaling the same?
In the scale is the same, but in the independent case, you have more control to understand what the maximum behaviors look like. Because if the maximum behavior is due to particles very distant apart from each other, you can kindly count in your process this kind of the second largest one, the third largest one, and then you find in the end your very gap of dependence particles. I kind of trying to understand what's the behavior of the second maximum, second particle. Yeah, you get?
Yeah, so the second particle, it has the same scaling as well. And that is also the case in the independent particles. So this result also applies to independent particles, because what we show is that we just have to show a subset of what we show for the exclusion system for it to apply to the independent particles. I think of it as like the negative correlation means these particles are spreading out, and they are eventually diverging. The difference between the second and first is diverging.
But how many particles you have to diverging till you find your core of particles? Yeah, your amount of particles. In the sense that what you see is your block of particles that never get out. Then you see a little particles far apart.
So if you take any consecutive one, so no matter how big M is, they'll diverge. Their difference between them eventually will diverge. Does that make sense?
Yeah.
So yeah, so if you compute the limiting means of these in terms of M of these distributions, they only depend on M. And even actually, sort of interestingly, even if you have more general jump distributions, it doesn't depend on the jump distribution or even the initial condition. So what's happening is, since you're scaling by this BT, this is sort of the rate at which they're diverging. And that's true for any M.
So, okay, yeah, I get it.
Does that make sense?
You don't have speed in these distributions. You have convergence. Like you cannot say T depend on M.
Right. That's
okay.
true. Yeah.
Thanks.
Yeah. So an interesting question though is, if you make M depend on time, what other sort of results could you get, right? So, is there a certain rate at which M can diverge, at which you see behavior that looks like, if you were at stationarity with the particle everywhere or something like that would be a question.
Yeah, thanks. Good talk.
Thank you.
So, can I ask a question?
Sure, please, Milton.
So,
go ahead.
Yeah. So, well, first, thank you very much for the very nice talk. It was really nice. I think we all learn kind of different things that we were used to. And so you mentioned a little bit about the Tracy Widom and the other type of fluctuations. So this was I don't remember if this process, this sort of Gumbel cloud is a determinantal process. The question is, if you remove the parameters of the asymmetry already in the limit, do this process converge one to the other?
Yeah, that's a good question. So it's like a weak ASAP result or something like that. Is that what you mean?
Yes, yeah, exactly, something like that. Yeah.
Yeah. So I think maybe so it would depend on the rate. I don't really know, but that's a good question. Like, can you get a Gumbel limit from sending the parameters in ASEP to a half or something like that?
Yeah, something like that, for example. Yeah,
I don't know, but that's interesting. I think there's definitely potential. So the problem is, so you don't for fixed T, right? You don't have. I apologize. Let me find where I was. You don't have this property, right? So this strong Rayleigh property applies to symmetric. So, and we're using it for finite fixed T. So you wouldn't have this property to work with, but that doesn't mean, so you need different methods for this ASIP result. So this they have they use formulas for finite time that they have for any order statistic. So in theory you could analyze those formulas, see what happens in that limit. For this case, I'm not really sure how you'd go about that.
I can comment that even in the Tracy Widom result, it's stated for the nearest neighbor case.
Mm-hmm.
So if you had non-nearest neighbor but with a drift, then that's an open question as well.
Mm-hmm. As is the this case with so this really relies on there being a particle everywhere to the left of the origin. If, say, you had alternating where there's a hole at every other spot, you don't expect this order 1 behavior because there's room to move to the left. So that also is something that is interesting to think about.
Thank you.
Thank you.
There are other questions from the audience? If not, why don't we thank Michael for a very nice talk, and thanks, Michael.
Thank you. Thank you for having me.
And so why don't we meet next week, and we can maybe close the seminar. Thanks again.
Thanks.
Thank you.